Hi students, welcome to our physics class. Our chapter name is Magnetic Effects of Electric Current. In the last class, we discussed about the working of electric motor. Electric motor. We completed that topic and today we are going to discuss the further topic in this chapter. In the last few classes, we discussed that within a conductor, when electricity is flowing through that, then what happens? They produce magnetic field around the conductor. They produce magnetic field. After that, we studied when there is magnetic field north and south is there, and when we place a conductor in between this magnetic field north to south is there, then what happens to the conductor? The conductor will move to particular direction. These all things we already discussed, and now we are going to study something different. Actually, this phenomenon was first studied by Michael Faraday, and that is something different. Before that, first you want to study what is this galvanometer. Galvanometer. What is this galvanometer? This is a type of meter similar to our ammeter and voltmeter, like that. This is also a meter that we are using in electric circuits. Now the question is, what is this galvanometer? What is this? This galvanometer is a type of device that we are using to identify the presence of electric current. So, this galvanometer is a device used to identify the presence of electric current I. And you can see the diagram of galvanometer in the page number 234 in one yellow column. That is what? The galvanometer. You can see that is in a particular shape and having a meter there and one needle. Normally, when there is no electricity is flowing and it is having two knobs other, and we are connecting this wire to this, and just leave it. So, here it have one needle, I already said. And that needle is always pointing to 0 when there is no electricity is flowing through the galvanometer. That means when there is no electricity, then it will be, the needle will be like this. The needle will be like this. And when the electricity is flowing, it will be moved either to left or either to right. Either to left or either to right. So, we can say this is used to identify the presence of current. That means when the current is flowing through a particular circuit, then you can see they are having deflection will be there. When there is deflection, we will identify that there is having the presence of current. That means through that circuit the electricity is flowing. That is the one thing of this galvanometer. And the another thing is that I already said that it is either be the to left side or right side. Actually, this is moving according to the direction of the current. We know the current can flow in both directions, to this direction or this direction. So, this galvanometer reading is to left or right, means that is representing the direction of the current. So, when we are studying about the galvanometer, you want to remember that galvanometer is a device used to identify the presence of current, electric current. That is the first thing. The second thing is this, we can use this to identify the direction of current. These are the two things that is done by this galvanometer. And actually this galvanometer is very sensitive. And when we are giving high amount of current to this, what happens is that the needle will break and then it will not be work. So generally we are connecting this galvanometer in circuits with a resistance with this circuit. That is, we will discuss when we are in lab. So now just remember, this is a device used to identify the presence of current and also it is used to measure or identify the direction of current. Just put it in your mind. And we are notating this galvanometer in circuit with a circle and one arrow like this. This is what? The symbol of galvanometer. Now two lines, only one line. This is the symbol of galvanometer. One circle and one arrow. This is the symbol of galvanometer. So now we are going to study one phenomenon. For that, I am just selecting a experimental setup that this is what? One coil. Within this coil, I am connecting galvanometer. And we are not connecting any type of battery or electric source in this solenoid. This is one solenoid and we are connecting one galvanometer here. Only we are connecting galvanometer and a coil. And this coil is having number of turns. Then I am placing here one magnet. Bar magnet. This is north and this is south. So when that magnet is out of the coil, in this galvanometer there is no fluctuations or deflections are occurs. And when this magnet I am just moving inside the coil, when I am moving this magnet inside the coil, you can see that here occurs a deflection. Here occurs a deflection and that deflection is in the direction of the right side. So I am explaining this like that. We have one magnet, just observe this, this is the magnet, and when this magnet I am moving to this side, then the needle at first is at 0 and then when this magnet is moving inside, that is this magnet is coming to this, you can see that this needle is moving to this direction. But simple deflection and then come back. And when this magnet is resting inside this coil, there is no deflection occurs. And now still this magnet is rest in this coil and now I am going to release this magnet. That means I am putting this back, moving this magnet back. At that time you can see that this needle will move to this side. That means at first our needle moved to that direction and at second time it moved to this direction. So we are saying when the magnet is moving inside the coil, that is moving to this direction, and when we are leaving this magnet to outside, then again there have one deflection. This deflection means, what is the meaning of this? We said that this galvanometer is a device that detects the presence of current. So what is actually happening here? Actually, because of the change in the magnetic flux, when we are moving this magnet inside the coil, what is happening there? This is a conductor. Within that conductor, the magnetic flux is getting changed with the conductor. So there is producing a current. There is producing a current. And who is producing this? It is produced by this magnetic flux or magnetic field around this magnet. So we can say here induced current. This induced means here produced current. So this is what the experiment. We done this using one electric coil, galvanometer and magnet. And The experiment is very simple. When the magnet is at outside, there is no deflection. When it starts to moving inside this, that means when it is moving, this is getting deflected. And when it is in rest inside this, there is no deflection occurs. And when this magnet is going back, that means again this magnet is moving, then you can see here deflection. Next, I am repeating this experiment with another setup, not another setup, I am just adjusting as first we moved the magnet. This coil was stationary or this was still and this was moving. In the second case, I am doing that this magnet is still or it is stationary. That means this magnet is fixed there. And we are taking this coil and moving to this. And then leaving to back. That is the second setup. At the same time, here you can see the same result occurs. That means that magnet is still there, it is fixed there, and when this coil is taken and moving towards the magnet, what you can see? You can see that this galvanometer needle is moving to right side. And when we are putting that coil stationary there, no deflection occurs, and when we are leaving this coil backward, you can see that the needle will move left side. So, in both of the cases, that means actually there happens the same thing, but at the first case, this coil is stationary and magnet is moving. In the second case, this magnet is stationary and coil is moving. So, in the both of the cases, they produce electricity or they induce electricity because of the change in the magnetic flux around the conductor. Because of whom? Because of this magnet. And next I am going to do something different, that turn the magnet twisted. That means here the south pole and the north pole. When we change the polarity of the magnet, then you get the result as, at first we get the magnet move to left side. The galvanometer move to left side. Rather than here when this magnet is moving, we get the opposite result. That means at first it will move to left, and after that when the magnet is in the stationary there is no result, and when it is going outside you get the needle deflected to right side. That means when the magnet is getting twisted or the polarity is getting changed, what happens? The current produced in the inside this coil is getting changed or reversed. So here we are saying that they produce or they induce a current, and I am calling this phenomenon called electromagnetic induction. Electromagnetic induction. So what is this electromagnetic induction? Actually this phenomenon is invented by Michael Faraday, and this is what the electromagnetic induction. This is the experimental setup. I hope it's clear for you. Nothing is there. We have one coil and galvanometer. Whenever the magnet is moving towards the conductor, they produce electricity. Or when the conductor is moving towards the magnet, then also they produce electricity. So, we can explain this electromagnetic induction as whenever there is a change in the magnetic flux, whenever there is a change in magnetic flux. Magnetic flux means the magnetic field lines, the same thing. So whenever there is a change in the magnetic flux linked with the coil, electricity is induced. So So this is called electromagnetic induction. That means whenever there is a change in the magnetic flux, that means when we are moving the magnet, what actually happens? There occurs change in the magnetic flux. And where there is the magnetic flux is linked with the coil means when the magnetic flux is getting contact, or when that magnetic flux is getting interact with the coil, and if that magnetic flux is having a change, then what occurs there? They produce the electricity or the induced electricity, and this is called electromagnetic induction. This is the definition for the electromagnetic induction. I hope it's clear for you, and there is something more about this. We already said that we have coil is the, galvanometer is the, and magnet is the. So, when the number of coils are getting increased, then the deflection here produces is also getting increased. That means when the number of coils are increasing means they produce more electricity. That is the one thing that depends upon the induced current. The second thing is this, when the power of the magnet increases, then also here the deflection increases. That means whenever the magnet is higher power, then the induced current also having higher power. In the similar way, when we reduce the number of coils, then what happens? Number of coils reduced means here the current also getting reduced. And when we are using a weak magnet here, then also the deflection is less, and so we can say the induced current also less. So we can say it as, according to the relation, when the number of coils in the conductor is directly proportional to the induced current. The number of coils means the number of turns in the coil. Number of turns in the coil is directly proportional to the induced current. And the next part is the power of the magnet. Power of magnet also directly proportional to the induced current. That means when we are using high power magnet, the induced current also high, and when we are using a weak magnet, then the induced current will be also less. So these are the things that related to the electromagnetic induction. Then next we are going to study with another setup. That means we are replacing, in first experiment we used magnet. Now I am going to replace that magnet with one circuit. That is our next topic. So this is related to the same electromagnetic induction, and a small variation is there with the name, and now we are going to discuss that. For this we need one cylinder. This cylinder is non-conducting cylinder. Non-conducting cylinder rod. We are taking non-conducting cylinder rod, and then here taking some copper wires and making a coil, and then connecting here battery, and then one key is placed. This is our first coil, and the next coil is this. Again the copper wire with number of turns are there, and placing one galvanometer. This is our setup. That means here we have two coils, and For this coil, we have one battery and a key is there. And in the second coil, there is no power supply we gave. And we have coil and galvanometer. So, this is our setup. And when we are using a conducting cylinder here, when I close the key, then what happens? Then that electricity will flow through the cylinder and will influence this. So, for avoiding that, we are selecting non-conducting cylinder. Non-conducting cylinder. That means this is non-conducting material. Even if it's a paper or something like plastic or anything. So, this is our experimental setup. And then, actually, just observe that in our last experiment, this setup is there. And what is there instead of this? We placed one magnet. I just thought that that magnet was kept at this side. And if we are keeping at this side, it's okay. So, instead of that magnet, we are placing one circuit. And we know that when electricity is flowing through one conductor, what produce the? They produce magnetic field. That means this is what? Electromagnet. So, we are using electromagnet instead of permanent magnet. That is the setup. And here we have one coil is there and we have another coil is there. And this coil 1 is this and coil 2 is this. And this coil 1 and coil 2 having names. And for the first coil, the name is this. This is the primary coil. This is the primary coil. And the coil 2 is what? Secondary coil. So, in this experimental setup, we have two coils. And in one coil, we are connecting the battery and the key. And that is the first coil and we call it as primary coil. And in the second coil, there is no electric power supply is there, but we are connecting only the galvanometer. And that is the coil 2 and that is called secondary coil. When now we are closing the key here. And then what happens there? Here also you can see when the electricity is flowing through this. That means when the circuit is complete, you can see at that instant there occurs a sudden fluctuation or a sudden deflection occurs in the galvanometer. That means a sudden change occurs and back. And when now the electricity is continuously flowing through the circuit and then no change will occur there. Now I am going to off this. That means I am opening the key. Again, you can see a sudden variation in this galvanometer. For example, when first I close the key, this galvanometer needle is moving to left. We are just supposing. And it just moved to left side and back to the zero position. And now the electricity is flowing, no changes occurs there. Now what occurs is that when I open the key again, you can see a deflection. But now this is in the opposite direction. That means the needle will move to this side and then back to the zero position. So here you can see that a continuous variation is the occurs when the key is on off, on off, on off. That means here when the electricity is flowing, what happens there? When the electricity is flowing, they produce magnetic field. That means when the magnetic field is produced there, that magnetic field, that means the change in magnetic field. At the initial stage, there is no magnetic field is there. And when the electricity starts to flow, there occurs a change in magnetic field. And that change in magnetic field influences the next coil or next conductor. And that's how they produce electricity and they induce electricity, and that's how they produce the deflection. And so when the continuously the electricity is flowing, there is no such change occurs. There have magnetic field is there, but there is no change with the magnetic field occurs, and that's how what happens? No deflection occurs. That is just standing still. And when we off the key, again what happens is that there have a magnetic flux is there, and then again there occurs a change in magnetic field, and then that change influences the second conductor, and again we get the next deflection. That is the thing happens here. The thing is this, the primary coil influences the secondary coil and here produce magnetic field. Actually this is something similar to the first case, but there happens is this, we are using one permanent magnet or magnet there, but here we are using a coil itself, and because of that coil the influence occurs with the second coil. And the similar thing is this phenomenon is also electromagnetic induction, but here we have two coils and we call this as mutual induction. Mutual induction. This is the another name for this electromagnetic induction, but the thing you want to remember that at the first stage we have only one coil, so we never call it as mutual induction. It is only electromagnetic induction, and if we have two coils present here, then we call it as mutual induction. And within this concept or within this diagram, how we can explain the electromagnetic induction? This mutual induction is something same for the electromagnetic induction, and only we are calling because of these two coils as mutual induction. So with this diagram we are now going to explain what is this electromagnetic induction. We already studied one definition for this, and now we are going to study the another definition for this electromagnetic induction. Electromagnetic induction. This is the process by which a changing magnetic field in a conductor. This is a process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. Electromagnetic induction. So what is this? It is a process by which a changing magnetic field in a conductor. In a conductor means a changing magnetic field in one conductor induces. Induces means produce a current in another conductor is called electromagnetic induction. For example, we already said that we have one coil, and that coil is having one battery is there and one key is there, and this is connected in one non-conducting cylinder, and here we have another coil is there, and here we connected one galvanometer, or if you are connecting here one bulb, you can see that it is just getting glow and then again off. So you can do this experiment using either bulb or with this galvanometer. Our aim is to identify the presence of the electric current. That is the thing. So now I am going to explain this using this diagram. It is a process by which a change in magnetic field in the conductor. When I close the key here, the current is flowing, and when current is flowing, what happens there? There produce a magnetic field, and there also occurs the change in the magnetic field. It is a process by which a change in magnetic field in the conductor, this conductor, induces a current in the another conductor. That means this circuit compels this to produce current. That means when here the magnetic flux is changing or there occurs a change in the magnetic field, then what happens? in this they induce or they produce electric current. This is what electromagnetic induction. Very simple thing. I hope it's clear for you. Now, we said that here the current is produced. Now the question is, what is the direction of that current? We already said that the needle is moving to that direction, to this direction, left, right, like that. So, now the question is this, which is the direction of that induced current? We use the left hand Fleming's rule for the identifying the direction of the conductor when that is placed in the magnetic field and current. Now we are going to study another law that we want to identify the direction of the induced current here. This is similar to our Fleming's left hand rule, but here we are using right hand. So the law is this, Fleming's right hand, Fleming's right hand rule. In the previous section we studied the Fleming's left hand rule. This is right hand rule. So in this again we want to use our three fingers, thumb, forefinger and middle finger, and we want to stretch this in the 90 degree. That means we want to hold it perpendicular. But the difference is this, at that time we used left hand and here we are using the right hand. Now the question is, what is representing for this each finger? That is the question. For the thumb, it represents the motion of conductor. Motion of conductor. Thumb indicates the motion of conductor, and the forefinger represent the direction of magnetic field. Forefinger indicates the direction of magnetic field, and now we have the middle finger. Middle finger indicates the direction of induced current. So, this is the Fleming's right hand rule. We are using this to identify the direction of induced current within the conductor. That means when we are using one coil and when we are moving one magnet inside that, they produce current. We already said. So now the question is, what is the direction of that current? We can find the direction of the current using the Fleming's right hand rule. Just take your fingers. The thumb is here, forefinger is here and the middle finger is here. The thumb indicates the motion of conductor. For example, when the conductor is moving to this direction, then I want to hold my thumb here. And this forefinger is the direction of the magnetic field. And then my middle finger is what? The direction of induced current. That means the current have to be pointed inside the board. That is the thing. We already explained how this we are finding and all we discussed in our previous section about the Fleming's left hand rule. The same thing is here. The only difference is this, we are using here our right hand and these are the indications for the each finger. And using this we will find how this induced the current having the direction. Very simple thing, and there is no questions to find the direction and all. You just want to put it in your mind. And you want to study the definition of the electromagnetic induction and also the mutual induction. And so this is all about this, and here we put our fingers perpendicular. That means they are, the angle between all these fingers are 90 degree. That means our conductor and the direction of magnetic field. That means if our magnetic field is in this direction, then our conductor have to be moved perpendicular to this. Our conductor have to be move perpendicular to this, then only the current will flow in higher value. And that's why we are putting our fingers in perpendicular direction. That is the only thing you have to put in your mind. So, in our today's class, we discussed about the electromagnetic induction and also the mutual induction. In your textbook, they don't give the name as mutual induction. They together give this as a single thing as electromagnetic induction. But actually, that is not like that. When we are using a single coil, that is electromagnetic induction. And when we are using two coils and when the first coil is influencing the second coil, then it is actually called the mutual induction. And also one thing is we said that the current induced, the process or the phenomenon is called electromagnetic induction. What is the name of that current? The name of that current produced is called induced current. Induced current, that means the current that produced when the magnet is moving or the conductor is moving is called what? The induced current. The name of that current is induced current. And when there is current, there is also having voltage. Now the question is, what is the name of that voltage? The name of that voltage is this induced EMF. The induced voltage is called induced EMF. So just put these names in your mind. Induced current is the and induced EMF. That means the process that occurs is the electromagnetic induction. They produce the induced current. That means that we are forcing to produce a certain current within the conductor and that current is induced current. And this induced current produces voltage and that is called, or the induced voltage is called induced EMF. Just put these names in your mind. Then take your textbook. You can see in the page number 236, electric generator. Now that is not there in your syllabus. It is cut off. And then in the page number 237, the domestic electric circuits, that is also not there in your syllabus. So our chapter is over here. In this chapter, it was a long chapter and we discussed about different things about the magnetic field effects and all. And we first discussed about the magnet and the magnetic field lines. And then studied about the magnet and its properties, the difference between the permanent magnet, temporary magnet, all the things. Then we studied about the magnetic field within a conductor, that is straight conductor, then the circular conductor. After that we studied about the solenoid. After that we studied about the right hand rule. Then we studied about the Fleming's left hand rule. All the things we discussed. And after that we studied about the force that is acting within the conductor when we place that conductor in a magnetic field. The thing that we discussed in our last physics class. And after that we discussed about the working of electric motor, that is very important, and we discussed that. And after we discussed about the electromagnetic induction, our today's topic, and this is all about this. Nothing is there. If there is a conductor and there is no electricity, but still when we are moving a magnet inside that conductor, what produce? They produce electric current, and that current is called induced current. This is the only thing we explained today. You want to read your textbook 3-4 times and we will meet in our next class with the next chapter.